For centuries, traditional mathematics has treated prime numbers as isolated dots scattered randomly across an infinite straight line. Because no exact discrete pattern has ever been found, mathematicians analyze prime distribution using continuous averages, relying on tools like the prime number theorem to describe the average density of primes among all positive integers. It smooths out the unpredictability, but still treats the exact location of the next prime as essentially random. The COREZERO framework abandons this linear model. It operates on the premise that numbers are vibrational states contained within a closed, cyclic geometry. By transforming the infinite line into a repeating loop, we stop evaluating primes by their arithmetic size. Instead, we map them using spatial coordinates. Taking a flat sequence of numbers and rolling it into a closed cylinder shifts the mathematical perspective. Under this geometric lens, primes emerge as predictable structural anchors rather than random anomalies. This number line coils into a modulo 24 cyclical system, revealing the prime cross. Every prime greater than 3 lands on exactly 8 spokes: 1, 5, 7, 11, 13, 17, 19, or 23. 12 is the central axis of symmetry. These specific landing spots are defined as COREZERO anchors. They serve as geometric fixed points that determine the exact location and stability of any given prime. Within this framework, multiplying two primes is treated as a spatial operation. It is the process of overlaying two distinct sets of geometric anchor points onto one another. If prime multiplication is a process of spatial geometry, reversing that process, factorizing a large number, could be executed through a rapid visual scan of those overlapping coordinates, rather than relying on slow computational division. To test this, we can track the prime number 11 using the system's state vectors, mapping its mathematical phases sequentially from A1 through A4. This diagram illustrates the A1 state notation. The positive sign represents an expansive phase. 11 acts as a starting coordinate for its future product, 77. In state A2, it reflects into negative space, shifting to negative 11, which targets the expansion product 55. The math mirrors the geometry. The equation 11 equals negative 1 plus 12 shows that the prime number oscillates exactly around the 12 axis, placing its mathematical inverse at position 13. In the subsequent A3 and A4 states, the system introduces neutral/probability, or NP, variables. These variables represent a point of quantum-like superposition where the number pauses before the mathematical cycle begins again. Analyzing a prime number through these 4 sequential states strips away its static arithmetic value. It behaves as a dynamic, predictable, harmonic oscillator mapped tightly to a grid. The system categorizes complex prime products, like the number 77, as high-state systems of the first order. 77 aggregates the distinct geometric properties of its foundational factors, 7 and 11. Multiplying 7 and 11 merges their individual 8-point configurations, creating a dense 16-point anchor structure locked directly onto the 24 wheel. We can calculate the A1 trajectory of the 77 system by expanding its primary base state. 7 multiplied by its product, 77, generates the value 539. Watch how modulo 24 geometry domesticates this number. Dividing 539 by 24 leaves a perfect remainder of 11, routing the calculation securely back onto the established prime cross. Secondary state interactions provide further proof. 11 times the next sequential prime, 13, equals 143. 7 times 17 equals 119. Both 143 and 119 geometrically reduce to position 23, acting as symmetrical, deterministic landing points on the opposite side of the wheel. These high-state systems suggest that the apparent chaos of large prime products is an illusion. Their growth is bound and precisely routed by underlying symmetry. The framework relies on deterministic recursion to find the root of these complex numbers. This visualizes the source equation, 77 equals 29 plus 48. 48 represents exactly 2 complete 24-step revolutions. 77 unwinds mathematically to reveal its origin point. That inner number, 29, is the core identity. It serves as a stability point from which the system expands. The next step of recursive subtraction moves into negative space. Subtracting the 48 offset from 29 yields negative 19. That resulting negative 19 links the equation back to the primary anchors. Reducing the prime number 5 by 1/24 cycle equals negative 19. Shifting the negative 7 across the 12 axis also equals negative 19. Deterministic recursion provides a blueprint for mapping these pathways, suggesting large prime products remain linked to their foundational cores through symmetrical steps. Modern data security, specifically RSA encryption, relies on the computational difficulty of factoring large prime products. RSA encryption is a cryptographic system that secures data by multiplying two massive primes together, creating a product so large that reversing the division takes conventional computers thousands of years. But COREZERO bypasses arithmetic division. It treats the act of factoring as a problem of geometric deconstruction. According to the theory, a prime product retains its original factors as a structural residue embedded within the product's 16-point geometric anchor system. An algorithm designed to visually scan a product's geometry could theoretically decipher these overlapping coordinates. It would reveal the two distinct 8-point shapes of its prime factors without calculating a single division problem. If algorithmic geometric scanning proves more efficient than arithmetic division, the mathematical walls protecting digital data would face a new type of structural vulnerability. This geometric hypothesis exists alongside breakthroughs in analytic number theory, notably the research of mathematician Ken Ono. Ono proved that primes act as solutions to continuous partition functions, demonstrating predictive order without needing traditional divisibility checks. A partition function is a mathematical formula used to calculate the number of ways an integer can be represented as a sum of smaller positive integers. While Ono uses continuous analytic waves to locate primes, COREZERO applies discrete cyclical geometry. Both frameworks strive to isolate the structures governing prime distribution. This terminology of high states is mirrored in astrophysics, specifically regarding AMCBN star systems. AMCBN systems are binary stars, where one white dwarf strips helium from its companion, creating a permanent energetic high state through orbital resonance. Prime numbers may not be isolated particles, but rather the predictable results of a geometric system that dictates their distribution throughout mathematical space.